Thank you so much, Nikki, and thank you everyone for taking the time to join us today. As Nikki shared and you've seen in the invite, we will be talking about the artificial intelligence, the basics, concepts, and its application to business. I will get into more depth on the specific objectives. I realize that we're in unprecedented times, and I realize everyone is have very busy schedules. So we do greatly appreciate the time that you are taking today to learn more about artificial intelligence. So I always start with this graphic because the hopes is that by the end of this session we'll have done what was commonly done to Neo in the Matrix, where we're actually transferring information from the outer world into our brains. Obviously, hopefully, we'll do it in a less invasive way. Um, but we do hope that you'll get a better sense of what AI is. I also use this slide, this image as well, is because I think there's a general misconception of what artificial intelligence is. I think many times people think is what we see it in the movies, and the fact is that artificial intelligence is in common practice today, as we'll learn, is and common business practice anyway, is what we call artificial narrow intelligence. So what we see many times in the movies, so whether it's iRobot, The Matrix, 2001: Space Odyssey, etc., that's what we call artificial general intelligence, and that's where a machine has the intelligence to apply to any problem rather than a specific problem. But what we're computing today, in most cases, and we'll learn more about machine learning and deep learning, but is what is the use of what we call artificial narrow intelligence. And this is where intelligence that equals or exceeds our intelligence as humans, but at a efficiency at a specific task. So artificial narrow intelligence, specific task that equals or exceeds our intelligence. General intelligence is any problem, and then there's artificial super intelligence, which is still um, potentially decades out, and this is where essentially computers become smarter than human brains. And again, we haven't achieved that. Everything that computers know today is what we've told them to know, or they've learned through algorithms we've programmed to tell them to know. So we'll learn. So our focus today is going to be on what we practice today, what we know, which is artificial narrow intelligence. And one of the major misconceptions about artificial intelligence is this common fears that we're going to be replaced by machines. I always, when I provide this presentation, I always liken it to where our forefathers or grand ancestors were sitting, 150 years ago. 150 years ago, if I said how many of you attending today are farmers, the majority would raise your hand. Today, if I was to say how many of you are farmers, in fact, most would not, right? And the fact is because technology has evolved and the way we farm and agriculture itself has continued to evolve through mechanization and to some level industrialization. And it's the same thing with technology. Artificial intelligence will, in some cases, make some jobs obsolete, but in most cases, what it's going to do is it's going to change the way we do our jobs. So I like to share this because some people, as you start to walk through artificial intelligence, you see that not only is there growing concern of trying to understand it, but hey, what is it going to do to my job? And most likely, there are some jobs that will again move towards obsolescence. There'll be a number of new jobs that are created. Right, 50 years ago, the number of jobs that we have today, a good 20+% of those jobs didn't exist 50 years ago, and it'll be the same 50 years from now, or even sooner. But again, the majority of the jobs, as we'll see, it'll be tasks that change within those jobs. So it's like moving from a typewriter to a computer, and from a computer to a voice-assisted mobile device. So, and that's what we expect to see. So a little bit about myself. I also am a Georgian resident. I live in Chattahoochee Hills, Georgia, about 45 minutes south of Midtown, for those who are familiar. Um, I've been in the technology industry for over a quarter of a century now, primarily focused on training and educating other professionals. Um, I I enjoy doing what we're doing today, is sharing knowledge that we have. I'm a business professional that has a passion for technology, including artificial intelligence. And we hope to be able to share some of that information with you today. The company I work for is CertNexus. We are a small global company that provides vendor neutral emerging tech certifications. So people that want to validate their skills and knowledge for internal or external marketability, or just to validate what they know. That's what we do. We work with organizations across the world. These are just some of the various multinational corporations we've had the pleasure of working with to help train and certify their individuals. And this is our roadmap. And I share this because this gives you an idea. We focus on, as I said, emerging technologies in cybersecurity, IoT, data science, and AI. And we actually have different levels of accreditation. We have ThinkLayer for business professionals and Build and Secure for technical professionals. And what we'll be focusing on today is a portion of our, what we call our AI Biz, or AI, artificial intelligence for business professionals. So this is a snippet of this course. It leads typically to a micro credential. We are going to give you free access to an assessment that would provide that credential if you'd like to, and then you can add that credential to your LinkedIn profile or other social media platforms if you choose to do so. So what are we going to learn today? What we're going to provide is a high-level understanding of the components that make up AI. So what are the basic terminology and concepts? And then the approaches to machine learning and deep learning. And as you'll see, machine learning is the most common practice of the concept of artificial intelligence today. So let's start with the basic concepts. And in doing so, I always like to start with the history. Artificial intelligence has this interesting history that unlike most technologies which have had this slow progression to an inflection point, artificial intelligence had a period of what they call the AI winter. And they actually experienced two of those. If many of you who are familiar with Alan Turing from the UK, he originated or created the Turing test, or invented it in 1950, in their 1950s. And that was really their first origins of what we consider today artificial intelligence. It actually got the moniker of artificial intelligence at a workshop in Dartmouth in the mid-1950s. And then in the early 1960s was its first application with Unimate, which was a robotic arm on a GM assembly line. And then moved forward with the first natural language processing application in ELIZA. And then it kind of all fell apart with Shaky. Shaky was the first AI robot. And what happened was there was a report that came out of the UK in 1973, the Lighthall report, which stated that we weren't going to realize the promise of AI. And so it really shuttered all initiatives for the most part around AI. So from 73 to the early 80s, there was no advancements within artificial intelligence. And then they realized there was an application of artificial intelligence around expert systems, something that could do a single task extremely well. And that advanced for about a half dozen years. But then with the advent of the personal computer, it fell off again because people realized personal computers were, again, more capable than these expert systems. So then we had the next winter of the AI winter. And then in 1997, IBM, as many of you may be familiar, IBM released Deep Blue and infamously beat Garry Kasparov at a game of chess. And that really started to set off what we see as the current evolution or revolution of AI. And that next went to Kismet, which was a head-shaped robot. The Grand Challenge, which was out of DARPA here in the US, which was for an autonomous driving vehicle. The first year, there was no car that was able to complete the circuit. The second year, there were several able to do that. And then in 2011, IBM released Watson, which now went on to beat, again, a champion, this time a Jeopardy champion, Ken Jennings and Brad Rutter, in a game of Jeopardy. Siri was also released with Apple at that point in time. And then we've continued to see the progression. And then probably again, one of the most extensive uses of AI is DeepMind from Google, which is able to do again more complex calculations than either Watson or Deep Blue did in its origin. And that really sets us up for where we are today. The fact is, the use of the technologies advanced much more quickly than anyone anticipated, and is pervasive through all industry sectors and use across all functions of organizations. As we'll see, it's it's marketing, sales, it's operations, it's manufacturing. It is pervasive and growing more so in all types of business and our personal lives as well. So what is artificial intelligence? Really, the definition of intelligence is debatable, right? A computer does not have intelligence. Humans and other animals have intelligence. And that's right, a computer doesn't really perceive its own environment. We program it to be able to do certain things that mimic its ability to do so, but it doesn't know how to do that yet. And we tell it it doesn't have the ability to independently yet to fully obtain knowledge and apply it for problem solving. Again, we're essentially providing its power to do so. So really what we look at it is from a scientific perspective, which is creating what we call operating machine intelligence. So really what we are doing and we'll learn is artificial intelligence being an umbrella term, and machine intelligence being what we commonly refer to as artificial intelligence today. It is a broad and somewhat technical concept, but really what we'll do here is we're going to kind of break it down so we can understand its components and how to best leverage it. So we're going to start with machine learning. Machine learning is it's an artificial intelligence disciplines that allows us to make predictions about an environment based on a given set of data. And so it's really important because the algorithms that we'll learn about in machine learning and the ways that we can train them it's highly dependent upon the data that we feed it. And so the data being the volume of data to be able to train it appropriately, but also the accuracy of data. So you're going to see a lot of you'll see a significant marriage between data science and AI in its application as well. And the difference between machine learning and a traditional algorithm is an algorithm typically you will take it through maybe a series of if-then statements, but it doesn't improve. It just continues to give you an answer, right? It's I don't want to say it's binary, but it's somewhat is. Where with machine learning, the difference is that you're going to train the algorithm or the model, as we learn about. It will learn to evaluate or make predictions based on that. To make predictions. It'll then evaluate the predictions based on how it's been trained. And then it learns from that and will improve. So really what it is, if you think about it, it is an intelligent algorithm that we've programmed and trained to essentially create or generate this intelligence. So the fact is it not only makes intelligent decisions, it actually gets better over time making those decisions, where a traditional algorithmic set of code would not do that. And that's really what we'll learn starts to separate artificial intelligence and machine learning from what we know as traditional coding. Deep learning is a type of machine learning that makes decisions using multiple layers of information. So again, machine learning uses single layers of information, deep learning uses multiple. And these layers are arranged in a hierarchy. So where conclusions are drawn from a lower layer, as you can see here, will then influence the next layer and ultimately be processed by a more complex higher layer to make a final prediction. And so let's just use a photo here, right? We input an image of a photo. That lower level says, hey, I can identify shapes. I can identify triangles. I can identify, I think that's a rhombus. If I can, an elliptical item, etc. And then what I can do is the next level of the deep learning will then be able to say, hey, listen, that that those elliptical shapes are eyes, and that square shape, that may be a mouth, and that rhombus shape might be a nose, etc. Then it goes to the next layer and says, okay, hey, let me put all these essentially uh, items together, and let me just say, is this a human face or is this a face of a rabbit? Well, we can see based on the bottom, the prediction is that it's a human face. So again, this is the difference between machine learning, which we'll learn more about in a second. And machine learning is a single layer. We have data, essentially we train it to do, to identify specific information, it outputs, and again, we'll continue to learn. Where deep learning, essentially it's going through multiple layers. And as you'll see, deep learning is less, there's more computation power required to achieve it. And it's also less directive by the individuals. It essentially it uses much larger data sets and actually is programmed to essentially to learn without less involvement from the programmer or other individuals involved. So how do these concepts relate to one another? Well, if you look at it, artificial intelligence is that umbrella term that encompasses many different machine learning techniques. Machine learning is a subset of AI and is, again, the most prominent use of artificial intelligence today. So in many cases, when someone says, hey, I want an artificial intelligence solution, they're really thinking about, I want most likely a machine learning solution. And for those more complex problems, they may say, hey, you know what, I want a deep learning solution that, again, is a more advanced use of machine learning in its very basic state. So again, artificial intelligence, that umbrella term, machine learning, the most common practice of artificial intelligence today. Again, we'll take another look at that. And then deep learning, which again is for more complex use. There are some additional AI disciplines as well, and we'll touch on them a little bit, such as natural language processing and computer vision, et cetera. The full course that we deliver goes through all of those. We won't have time to do that today, but it gives you an idea that there are other for those who are familiar with AI, admittedly, there are other ways to leverage technology or implement using other forms of artificial intelligence or machine learning. So let's get to an example of machine learning versus deep learning. And I think this example will help bring home the difference between the two, and then why would you we'll look at why you would select one over the other. So it may, again, at face value, be difficult to grasp the difference between machine learning and deep learning based on just the definitions. So what we're going to do is we're looking at an example that looks at a new image of a human face. So the software is going to point out where the face exists in the image. And so in traditional machine learning, you give the machine several images and input. Some of these images will have faces and some of them won't. And then the faces, the images that do have faces will show different people, just to ensure that the algorithm has a spectrum of data to learn from. You don't necessarily need to tell the algorithm this is a face, this is not a face, but you still needed to give it some guidance. So you'll tell the algorithm what some of the characteristics, of faces are. So for example, a general shape to the overall face, the nose is at the center, you have two eyes with generally the same shape, you have a mouth, and many other types of inputs. And then the algorithm will use these characteristics along with the images you give it as input to form what it considers a face. And then another data set is provided to the algorithm. It uses the data set to validate its predictions. And lastly, you provide the algorithm with new test images, and it should be able to identify those images include faces too. So what happens is that first set of data is what we call the training set or training data. So again, we're giving it images, and again, this is with machine learning. We're giving it images with faces, without faces. various different types of faces, and we're identifying the labeling the components of the face so the machine can learn what a face is. Then we give it a test data, right? And what it does is it takes everything that it's learned from that training data and applies it and attempts to identify photos with faces. Again, what we may have to do is intervene and say, no, you incorrectly identified a rabbit as opposed to human. But then it will learn from that. So the next time they'll notice those long ears are not the same as the oval ears on the side of the head, and it will not identify a rabbit as a human. On the right-hand side, when we talk about deep learning, you don't give the algorithm any guidance. So to what the characters of a face are. Instead, you just supply the algorithm with the input of images. And the big differentiation with deep learning, it requires significant volumes of data. So on the machine learning, we probably could get away with doing allowing that algorithm to identify face from a photograph with thousands of images probably. Deep learning, it may require tens or hundreds of thousands or even millions. And what you do is you actually provide the algorithm with all the images, and you allow it to essentially start, the algorithm begins analyzing each image and placing different dimensions of the image into classification layers. So again, it starts simple, as we saw on the previous slide, right, with basic shapes. It then identifies those shapes as parts of the face. And then from the parts of the face, it actually will identify if they are within a face. And then the algorithm itself says, oh, okay, these parts, these essentially create a face, and this is a face. And thereafter, I'm going to now consider this essentially compilation of data as a face. So this really empowers deep learning to make determinations that in some cases even human experts aren't able to do themselves. So again, machine learning, typically smaller data sets. We typically provide some type of classification as we saying, hey, this is a face or this is not a face. We then provide more guidance to it. And again, it learns based on essentially being able to successfully identify a face. And when it does not successfully, it learns from that. Deep learning, we're giving it a lot of data. That data is the algorithm is classifying that data itself. It's making unguided predictions based on the extract of that data. And then it's essentially coming up with what a face is. And again, this is really effective, as we'll see, at solving more complex problems. So machine learning versus deep learning. So, what's the choice? And it really comes down to what you're attempting to achieve. I spoke a little bit to this the last slide. And again, it doesn't matter the size of the business, it's really what you're trying to solve for and the data sets that are available to you. So if you are a B2C company, let's just say in banking, and you have tens of thousands or hundreds of thousands of customers, you may have larger data sets. If you're a B2B company and you sell to, let's say, hospitals, and you have 1,000 customers and you sell a smaller set of products, you're going to have less data points. So really you have to start with is, what are your data sets? Are they large and voluminous, or are they smaller? Then, so if they're smaller, it's obviously traditional machine learning is going to be a better option. Where if they're more voluminous or larger, obviously it's going to be deep learning, excuse me. And then, do you need to help to solve the problem, right? As an expert, do you know and we'll see some examples, but do you have the data, or are you able to help label or solve for what some of the items are? Or is it something that really it's the expert doesn't know, or you're really asking, in this case, the algorithm, the deep learning algorithm, to solve for that? And you can see some great examples of traditional machine learning, right? Examples are customer surveys, patient health records, bank account activities. A great use of this is in fraud, right? I also saw a AI application was used in the fintech industry, and it was around auditing expense reports, right? So people the company wouldn't allow for alcohol to be expensed. And so the algorithm went through, and anytime it saw anything that was representative of alcohol on a receipt, it wouldn't allow for that item to be expensed. Now it does have to learn the difference between root beer and beer, right? So for a while it was tagging root beer as an alcohol, and then over time it realized no, root beer wasn't, because it was provided, again, inputs by an external force saying, and typically a person saying, hey, no, that's incorrect. Root beer is not beer, therefore it's an expensable item. Deep learning is going to be for really much more complex problems. And again, it's a lot of times it's text to speech or speech to text. So you're talking about more, we'll call natural language processing and other types of uses for deep learning. Again, bigger data sets and bigger problems to solve for. So we're going to talk about some of the approaches to machine learning and deep learning. So machine learning, there's three primary types. There's supervised learning, unsupervised, and reinforcement learning. We'll take a look at each of these. So supervised learning is when you have it's an approach in which the values of the variables you're trying to predict are provided as the input. So what does that mean? It means there's typically the components are, there's an example, so which is an instance of a data, the feature, which is a measurable property, and the label, the item that you're trying to predict. So if we, and then you put this together and you use this to train an algorithm. So what does this look like? Typically, you could use data from an Excel spreadsheet, right? And so in this case, we have individual examples, right? We have these unique identifiers, which are the ID of each of the patients, according to GDPR, et cetera. Obviously, we're not showing their names or other identifiable information. But then we're looking at the features of that person, right? And those features are weight, height, and their blood pressure. And then what we're telling them is, do these patients have heart disease? And for some of them, it's no, and others are yes. But we're telling the algorithm in our training set of data is we're saying this is a person of this weight with this height and this blood pressure. They don't have heart disease versus these that do. So remember, so note that the ID here is not a feature because it's not relevant to predicting heart disease. What is the features and how we label that. So how that works is we start again with a set of training data, and we say, okay, here's people with good health, here's people with bad health. We run it through the algorithm, and the algorithm learns to classify that. So if I have, if I'm potentially overweight, or I have a history of heart health in my poor heart health in my family, or other indicators, we feed that information into the algorithm, and over time that algorithm says, hey, I understand it. If Jeff is 4 foot and weighs 500 pounds and has a history of heart health, and eats Fruit Loops for breakfast, and hasn't walked a step in a year, he's likely that he's going to have a heart health issue. Or I'm taking larger data sets of people that have all those indicators and including the label within that. So we provide that training data, and then what we do is we use new data. And again, this could be your test data, or eventually it's the data that you want to be able to define. So what happens is, now you input the data, the algorithm says, hey, I know this person has these characteristics, and it's likely to say whether they have good or poor heart health. So again, the algorithm's learning. Again, it's a prediction the algorithm's making. There is going to be some human checks on this initially to continue to repoint the algorithm back to the correct answer. Again, the rabbit face versus the human face, or root beer versus beer. But over time, the machine will learn and will make fewer and fewer of those errors. And over time, we'll have a near perfected algorithm to essentially, if not predict heart health, at least to be able to display what the likelihood of it is. Unsupervised learning is where you don't label the output. So, so what we've done is we will take a lot of the same items, right? So we're taking individuals, unique individuals, ID numbers. We're taking the features, right? So the features again could be height, weight. It could be other items. Now we're getting maybe a little less specific, right? It could be around exercise. It could be around diet. Um, it could be around stress at work, etc. And you have these essentially these unlabeled inputs, right, that you're inputting now, and the algorithm starts to learn the patterns. So and then what they do is they actually will cluster like examples, again being more predictive. So so really the big difference here is example is that the algorithm isn't explicitly told what it's to predict, which we did before, which is good or poor heart health. It, because instead it's in using this health record example, the column that records whether or not someone has heart disease would be not marked as a label for the algorithm to predict. So we wouldn't say is a good or poor heart health. It is maybe, are these people likely to be healthy or not, based on the data we've inputted, right? So we're not giving it the answer. It's coming up with the answer itself, or the prediction of that answer, I should say. So reinforcement learning is a bit different, and this is really the third main use. And I should say, if you look at it, you know, supervised learning is typically used. We talked a lot about the banking industry, et cetera. Unsupervised learning is more useful in areas such as customer segmentation. So where you can identify customers exhibiting certain behaviors, and then you can tailor their customer service or marketing approach to those individuals. So a lot of the unsupervised learning process is used in marketing automation, customer relationship management, et cetera, as far as applied business use. Reinforcement learning is used more often in robotics, or if in gaming, like chess, checkers, etc., where there's a typical outcome, and it's either right or wrong, and it's reinforced based on that. So that's exactly what reinforcement learning is. So essentially what happens is the algorithm selects an action from an available set of actions. So you can see here, we're selecting from a number of different chess pieces. We've selected the pawn. We move the pawn, so we've taken action on that. The environment changes in some way. So now you can see the pawn has, we've moved it, its two initial spaces. The reward for the action is calculated. So did that action result in a positive result or not? And if so, a reward is given, and again, the process repeats. And so you can see how this applies to robotics. It could also, again, apply exactly to what we're seeing here is a game of chess. So the idea, again, being that there's the three types of learning. There's supervised, unsupervised, and reinforcement. In most business practices today, outside of manufacturing environments, you're going to see more supervised and unsupervised. And again, it's going to be based on the data that you have, how that data has been engineered, and what you know going into developing the algorithm. Do you understand what the expected outcomes will be? Or are they still unknown to you, and do you want the algorithm to help define those for you, being the difference between supervised and unsupervised? Again, reinforcement learning, again, a great use of the technology, but maybe less applicable for some of your uses, common uses today. So now we're going to talk about deep learning, right? So if we look again at going back to those circles, we looked at artificial intelligence being the umbrella, conceptual concept of the technology, machine learning being the most common use of it today, and deep learning being the more advanced use of machine learning. So we're going to talk about three types of neural networks: artificial neural networks, or ANNs, feed-forward neural networks, and recurrent neural networks. So an artificial neural network, it's somewhat of a misnomer because we talk about intelligence, but again, computers really don't have intelligence today. And we talk about these neural networks because they're fashioned after the brain. In the fact that what we do is we use neurons, neurons. Those neurons are connected by synapses in our brain, and computers, those essentially neurons or nodes are connected by electricity, and they're grouped into layers. So we use brain-like terminology, but again, making the distinction that we've yet to create any type of artificial intelligence that is representative of the brain in its entirety. So it's the foundation of deep learning. ANNs were the original deep learning. What we'll see, which is going to be different here, is that the input, again, as we saw before, is processed in layers. And again, it's going to learn without explicit guidance. So again, more computing power, and more intelligence, if you like, or capability within the algorithms or the models selected. Again, what you're going to see is these nodes are going to transfer information through these layers, and the layers are going to perform specific functions, with each one of them becoming typically more complex. ANN is used again in many different industry sectors across, in performing a huge number of tasks. Everything from diagnosing diseases in patients, right? We're even seeing this, in our current health crisis with COVID-19. Companies that are coming up with potential cures or vaccines are using artificial intelligence to do that. We use it commonly in our business practices to identify malicious behavior as part of our cybersecurity defenses. So think about your email filters, and et cetera, endpoint solutions, and on and on. All of these now are starting to incorporate artificial intelligence. So becoming less reliant on the individuals that administer those or configure those environments, and more so on large data sets, which can say, hey, listen, this is not a typical email that would be sent to this person based on their profile, right? And in translating human languages. We all are big fans probably of Google Translate today. Allows us to talk to people all over the world through text and through voice. So the structure of an artificial neural network, there is composed of neurons and layers. So again, the neurons are nodes, are connected to one another, similar how our biological brains are, and they're grouped into these layers used by deep learning. So each layer performs a specific function and then shares its output with the other layers to create a really highly integrated platform for making intelligent decisions. So, and we talked about the ability to translate human languages, et cetera. It's also used in energy consumption management, resource management, and just a variety of technologies. So we're going to look at two neural networks that feed forward and the recurrent. So the feed forward is exactly that. Information moves in one direction, so it's unidirectional. What happens is with the layers, typically you'll have 3 layers or more. So you'll have the visible input, so where you're directly exposed to the input. You have the hidden layers, which are not exposed to the input, but essentially perform or require analysis, and then you have the output. Again, the original and simplest form of an artificial neural network, or ANN, is this feed-forward neural network. It's less computationally expensive. And really, one of the things I neglected to say up front is that really what we're bound by today with artificial intelligence is computing power, right? As we move towards quantum computing. That may release some of the constraints we have from a computational perspective on what we can actually do. Also, the data sets that we have available to us, but then also our own intellect. Are we able to create these more complex algorithms and models that will allow us to expand from narrow intelligence to general intelligence? And then there's a whole bunch of ethical and bias and security factors around that we won't get into today, which are of great interest and concern. And then feed forward neural networks are applied to complex pattern recognition tasks. Again, as a customer that has come to your site, are they likely to return and purchase additional products? So again, a lot of that intelligence that we're gaining through our e-commerce platforms, our marketing automation systems, CRMs, et cetera, as well as a large number of other systems in our environment that we use today. So this is how a feed neural network is shaped. Again, if you look at it, it's going to move from left to right. We have that input layer where we're inputting information. We have those hidden layers where that we have that computational power, if you'd like, and then we have the output layer. A more complex form of a artificial neural network is a recurrent neural network. And this is, so instead of limiting the flow of a single direction, this really allows information to move in cycles. So information at one layer can flow back to a previous layer. And this puts the neurons in a dynamic state and gives them something comparable to a memory. Again, we're using human-like terms here, but it's comparable to a memory. So the neurons then can incorporate calculations on previous inputs. For example, if there's a desirable, and this is desirable in situations where different inputs are dependent on one another, like in a sequential task. So for example, if you give the neural network the word learn, it will need to remember that E becomes before A in order to predict the next letters possibly are. And so, again, these are going to be more computationally expensive. So again, requiring more computing power. And again, one of the most common uses of recurrent neural networks is natural language processing. So the structure of a recurrent neural network, again, you do see, again, some of those left to right types of flows, but you can also see that they come back, they cycle back, right? So an output layer can go back into a hidden layer and again, go through that those models or algorithms to come back and to provide another output. Again, greater complexity, greater computational processing power, etc. There is one other type of neural network that we're not going to cover here, which is a convolutional neural network. It's where every neuron at one layer is connected to every other neuron in a layer. And these are really, they excel at recognizing and understanding images and other visual data. So it's another type of neural network, commonly used again with photos, images, etc., where you'll see feed forward and recurrent being the most popular uses in other business applications. So we're going to move into our Q&A portion of the presentation. Before doing so, one of the things that we would ask, even beyond the questions we're going to answer today, is what sort of additional research can you do to learn more about the concepts behind AI? Obviously, there's programs like ours that are available. There's some great websites. For those who don't know, MIT produces a AI newsletter, which is a phenomenal newsletter. I know there's other institutions within Georgia itself that do, as well as I'm sure there's other resources in the broader TAG community. But what I would say is, with AI is the concepts that we explored today and discussed are really the basic concepts. What really gets interesting about AI is its application or use. And and again, a lot of this information is, I hopefully that you have learned today will help you expand your research. The other thing to note, and it's not wasn't articulated directly in this presentation, is that most AI implementations, the success of those implementations are dependent upon three things. One is leadership. Does leadership really understand the opportunities and the challenges for the technology itself? Unlike traditional technologies, and not to pick on network operating systems, but if you're an executive, you don't really care if you're using Windows Server or Linux Server, right? As an executive, you care about the ability to access documents on your network, email, to browse the internet, etc. It's the capabilities of network operating systems that you're concerned about. And as long as it comes in budget, most don't care if it's Windows or Linux. With AI, we're entering a different realm of technology, because AI, as you can see, actually shapes how we conduct our business. The products we develop, how we develop them, how we make them available to market, how we engage with our customers, how we become more responsive to the needs of the customers who consume our products and services. So you really have to think about, hey, what is AI? What does it do? What's possible with it, and then actually starting to work at it from a business perspective, because the technology is there, it avails itself to you. It's essentially, are you making business decisions that allow you to best utilize that technology? And then the other, so that's one. The other big part of this is data. Data is, our modern currency, right? If you think about the companies with the greatest valuations in the world today, a number of them are based on data, right? They don't manufacture anything. They typically are not providing services that are leverage vast large of labor pools, et cetera. Essentially, Google being a great example of that, right? They monetize the data, right? So and it's the same with artificial intelligence. Employing the technology is making sure that you have representative data sets. We can talk more at a later time about ensuring they're ethical, unbiased, and secure. But then making sure that those data sets are used wisely and engineered for the best output or best decisions that these models can help you define and create to help operate your business. So with that said, I'll stop there, and we are able to take questions.